So this is a standard inventory control problem. It's highly simplified, but it should give you a flavor of the kinds of operations research problems that a business that is heavily dependent on logistics or supply chain management might be interested in, but this is a highly simplified version of that. Okay? So suppose you have a supermarket that wants to establish an optimal inventory plan for frozen orange juice that balances refrigeration and delivery costs. So the idea is that if the supermarket gets deliveries every day based on its expected daily demand, then it won't have to store very many cases of orange juice in the refrigerator. So its refrigeration costs will be lower, but it'll have to take a delivery every day. And there are labor costs and packaging costs associated with having lots of deliveries, right? So you will need to balance refrigeration costs against the costs of deliveries and packaging. Okay? So very often you might have to trade off those two, and how might you pick the optimal replenishment rate? Every day, once a week, twice a month, that sort of thing. Okay, so it's estimated that a total of 1,200 cases will be sold at a steady rate during the next year. Okay, so obviously it is a simplification to say that it'll be a steady rate. There's probably a seasonal profile to it. But you can actually add that complexity onto this and still preserve the structure of this problem. Okay. The manager plans to place several orders of the same size, equally spaced throughout the year. Again, a simplification. Use the following data to determine the economic order quantity, that is, the order size that minimizes the total ordering and carrying cost. Okay, so you're trying to minimize ordering and carrying cost. The more you order, the greater your ordering cost, but the less your carrying cost. And the less you order, the more your carrying cost, and the less your ordering cost. So order cost per delivery is $75. So let's say that's the cost of the labor to deal with the truck. Maybe it has built into it some levelized cost. Remember, we met the term levelized in the last session. Some levelized cost of packaging. Let's say it costs $8 in electricity to refrigerate one case of orange juice for 1 year. Okay. So what we're trying to do is to find the optimal order quantity. That is, we know that over the course of the year we're going to order 1,200 cases. That's the total demand over the course of the year. We want to know, are we going to order 1,200 cases one day in 1 year? Or are we going to order, make 3 orders, actually probably more like 5 orders per business day, and so on, right? So let that order quantity be called X. So that's the total number of cases that you order per order. N is the number of orders per year. Okay, so it's got to be the case that X times N is equal to what? 1,200, right? You want the annual order to be 1,200. So one constraint on our solution is going to be Xn is equal to 1,200. Then I know that the inventory cost is the total of delivery cost and refrigeration cost. Well, that's $75 per order. So there are N orders. So that's 75 times n, plus $8 per case of orange juice in average inventory. Okay, why in average inventory? Because once again, it's the levelized cost concept. Actually, in this case, we've sort of levelized it by design, because I tell you, to simplify, we're going to order the same amount each time. Okay? But what's going to happen? Let's say, suppose that I'm ordering 1,200. Suppose I order 100 units each order, and I put an order in once a month. Okay? So at the beginning of the month, I'll end up with 100 units in stock. Demand comes through at a constant rate. So my, by the middle of the month, my 100 units will go down to 50. And by the end of the month, my 50 units will go down to 0. Okay? And then the first day of the next month, I get 100 again. So let's think about how refrigeration costs would work. And this is, it's worth actually drawing that out over time. Okay, so let's say this is 12 months. This is time in months. And you're going to order, this is the order size, what did we call it? X, right? And also, so order size, actually, so that's not X. That's order size X is here, so that's how much you'd order at the beginning. This is inventory level. You're going to run that down, and the next day you're going to order another, and so on. Okay, and I should probably put one of those fancy things they do here, right? To say, we don't know how far away 12 is. Okay, well, this graph, it gives you the profile of inventory over time for any order size X that you choose, right? And because I've constrained my total orders to my total order quantity annually to be 1,200, if I choose an X, I also determine an N. Okay? Now, so what is the refrigeration cost associated with my choice of X? Okay, well, I can simply take the midpoint of each of these cycles, in other words, the average of this value and this value, and multiply it by $8, and I'll know what my total refrigeration cost will be. Does everyone see that? Because this unit, these X units are going to, I'm going to pay, I'm going to pay a refrigeration cost on them for, for a long time. But so let's say that every day I lose one, and let's say X was 30 days in a month, then the first unit, I'll lose it in 1 day, so I'll only pay refrigeration cost for 1 day. The second unit I'll pay for 2 days. The third unit I'll pay for 3 days, and so on. And it turns out, if you're interested in it, of course, it turns out that the total cost will be the area under this curve, which is going to be half times this base, or half times this height, or if you like, the average of this number and this, which is 0. So that's half of x times $8. Okay?
What does x represent?
X represents the... No, it represents your order quantity, how much you replenish your store with when you order.
So let's say if we order 101.
So, no, right, so let's say you order 101, but you, okay, so if you do that, then you'd end up ordering a little bit less than 12 times a year, right? Because your total order has to be 1,200. So let's say you order 100, okay? And you order 12 times a year. Then you're going to do it once a month, let's say. Beginning of the month, you order 100. Your refrigerator has 100 units of juice. And every day people come through your store and buy juice at a constant rate. So they're buying at the rate of 100 a month, right? So they're buying at the rate of 100 a month. You bought 100 at the beginning of the month. By the end of the month, you'll be at 0, right? So, yeah, so your inventory level, this is your inventory level. It starts out at 100. In the course of the month, it'll get to 0. And the next day, you'll stock it back up, and so on. But you want to know, okay, what's the refrigeration cost? So it's going to be, for those 100 units, there's going to be some units that, well, there's going to be some units that stick around for 30 days, some units that stick around for 29 days, some units that stick around for 28, and so on. If it sticks around for 29 days, then how much will be the cost? It's going to be $8 divided by 12. Because $8 is the cost to refrigerate one case for 1 year. So, so you'll have...
Is our average inventory 50?
Your average inventory is 50.
So it would be 8 times 50.
Exactly. Okay? So, on average, this will be your inventory. And you can just assume, without having to look at this or abstracting from this, you can just assume that your refrigeration cost is going to be, in that case, 50 times 8. But 50 is if we chose x equal to, so it's really going to be x divided by 2 times 8. That's for the whole year, yes. So this is annual inventory cost. Okay? And what is that? It's annual delivery cost plus annual refrigeration cost. Well, how many orders do you have in a year? N. How much does each order cost? 75. So that's your annual delivery cost. And that is your annual refrigeration cost. Okay, so setting this problem up requires a bit of thinking. You see, that's why I want you to understand the intuition behind this calculus, because setting up the problem, it's not a set of cookbook recipes. You can't just say, well, here's a function, I'm going to take a derivative and set it equal to 0, minimize or maximize. Life is not like that, right? Nobody tells you that here's a function that you have to take a derivative of, except in my midterm. But you have to set up a problem. You have to know what is the function that I've got to either find the minimum or maximum of. And that's what we constructed here. Okay? And it's not always going to be obvious. Sometimes in problem sets, you might tear your hair out a little bit to do this. Okay. But that's the way that real-world problems work. The practice you go through to construct those problems will help you. Okay. So here's the expression for annual cost. And here is a constraint that we know. We know that total demand is equal to 1,200. So we know that n times x has to equal that. Okay, well, you can actually, solve for n or x and substitute in here. Right, this is what we learned to do in the last session. Okay, so here I've solved for n and substituted for n in this equation. So instead of 75n, I have 75 times 1,200 over x. So that's 90,000 over x plus 4x. That's total annual cost as a function of x. X is a number that I get to choose. And I'm going to choose it now in the most optimal way possible. Okay, I'm going to choose the x that minimizes total cost. And I built into this expression both the cost that comes from refrigeration and delivery. Okay, well, now you know that, okay, I have to minimize this function. Now you know what to do. You can apply the cookbook recipe, which is what? I hear some muttering over there. Alan, do you want to tell us?
Take the derivative and set it equal to 0.
Okay, take the derivative of this, set it equal to 0, and find the values of x for which that's true, right? So we take the derivative here, just apply the power rule. This is really 90,000 times x to the minus 2, sorry, times x to the minus 1. So when I take the derivative, it becomes minus 90,000 x to the minus 2 plus 4. Set that equal to 0 and solve for x. And you will get, since this is x to the squared, you'll get a positive and negative root. Your answer here is x equals plus 150 or minus 150. But you can reject the minus 150 because you know what you've constructed x as. It's the order size, and it cannot be minus. Yes, you had your...
Why was it there?
This one? Oh, that's... So this is... recall your laws of exponents. And this is just from your primer. 1 to the x is the same as x to the minus 1. Okay? Or 1 to the x squared is x to the minus 2. Okay? Okay, so that's your answer. Okay, and if these numbers were different, let's say that 75, let's say that your packaging cost or your delivery cost was much higher and your refrigeration cost was much lower. Then what's going to happen? If your refrigeration cost is lower, you're going to want to keep more inventory and order less. So X is going to increase. Your optimal order quantity will increase. You'll tend to have higher levels of inventory on average. Okay? And this kind of relationship, so the price of labor or the price of packaging relative to the price of energy, determines choices that everybody, individuals, businesses, governments make about their business processes or about their energy demand, which obviously have impacts on the economy and thence on the environment. So here you've seen a sort of a full-blown example of a sentence that I used yesterday or at the orientation when I said the structure of a capitalist economy often almost completely determines the impact on the environment. Well, what is the structure of that capitalist economy? It's prices. Prices are central to market economies. So changes in these relative prices will change whether we're using more packaging and less energy, or more labor and less energy, and vice versa. Okay? Yes. Right. That's right. But you see, when you now in America, most supermarkets actually have an average life between renovations of 4 years. That's very short. Okay? So what that means is that when this relative price is determined, it affects supermarket design for the next 4 years on average. So these prices will affect how a large chain will determine how many refrigerators they're going to have. You know, it's not that you know, basically in the very short term, in the day-to-day analysis, of course, the refrigerator size is fixed. But when you start to scale back, you realize that these choices, these design choices, are themselves the result of these prices. And also they're also affected by interest rates.
This isn't really about the price of orange juice.
Actually, it has not. This is not about the price of orange juice at all. It's about the relationship between the price of labor and the price of energy.
Right.
That's basically the key trade-off that we're looking at.
Okay.
You know, if you
get with all your products that need.
well, when you design a new build,
Yeah.
you will have in mind that I want X percentage of my space devoted to refrigeration. And that percentage is going to be higher or lower depending on this trade-off. Yes?
Instead of your original assumption of 100 case per month, you...
Yes. And if this, say this was $4, I would go from 150, I might go to 200.
So in the span of 1 year, you're going to order
Far fewer times, but larger quantities. That'll encourage you to have more refrigeration space devoted to your new build the next time you build a new supermarket. Yes.
So if we were to incorporate demand.
Yes, and the real operations research problems like this are, you know, they're not toy problems like this, but nevertheless they have embedded in them building blocks that have trade-offs that look just like this. There may be lots of different trade-offs, but nevertheless the trade-offs broken down will be simple enough.
And you do another, would you do?
Yeah, but yes, but there are other complications. For example, you have some variables are not worth incorporating into your analysis, because even if you incorporated them, the impact on your optimal choice might be small. For example, it's generally the case that energy costs have been negligible in many American planning decisions because of the structure of energy costs in the US relative to everything else. But the nature of relative prices in other countries where there are heavy energy taxes means that their entire landscape looks different simply because of energy costs. You know, suburbs, for example, don't make any sense if you have gasoline at $6 or $7 a gallon, which is sort of close to a price in Italy, let's say. Okay. Okay. So it's almost 9 o'clock. There are lots of other examples like this in your slides. I encourage you to try at least some of them out. If you have problems, come and talk to me. Just a second, Kathy. Next time we will talk about multivariate functions, and we'll lop off a little from integration. Yeah.